Hello everyone, this is Mr. Chung. Now this is for the day 1 class only because the day 2 physics class has already covered the same topic. I just couldn't remember if day 1 did or not, but after a few emails, reminders, now I'm sure that day 1 class didn't cover this. Okay, so this is going to be one of those consequences of special relativity, specifically dealing with mass. Okay, so what Einstein has discovered is that energy and mass, even though we treat them differently in our physics class, is actually the same thing. Now, how are they the same? They are basically just two ways of looking at the same concept. So for example, there are actually ways that you can switch mass to energy and energy into mass. For example, one of the nuclear process that we rely on, which is the nuclear fusion of the sun, is actually a process that turns mass into energy or transforms mass into energy. For hundreds of years, scientists were wondering how come the sun never actually turned off? I mean, if the sun is burning and has been burning for 5 billion years, where on earth are the fuels coming from? Now, later on, we understand that is actually a process called nuclear fusion. Now, in nuclear fusion process, what happened is the sun is basically a giant ball of hydrogen gas, right? And when two hydrogen gas atoms, so you can see that I have two hydrogen gas atoms here. So when two hydrogen atoms under intense heat and pressure smash together, sometimes they have enough energy to actually join their nucleus together and become a helium atom, right? With two protons, right? Hydrogen has one proton, so two hydrogen together get you a helium with two protons. Now, this is like having two tiny Lego blocks and then you're trying to add them together, right? So initially, how much stuff do you have? Now, initially, we have hydrogen, right? So initially, we have hydrogen. Now, we have the mass of hydrogen and we multiply that by 2, right? So we have 2 hydrogen. That's your initial mass. Now, at the end, what do you have? Well, at the end, we have a helium, right? So it's the mass of a helium. Now, in normal circumstances, when you put two things together and join into one, for example, when you build something, you have two parts and you put them together and they become one giant part, the mass of those two should be exactly the same, right? I mean, that's what we would expect, like these two to be the same. But unfortunately, well, actually, in our case, it's fortunately, because if that wasn't the case, we wouldn't exist. This is not true. The mass of the two hydrogen is actually not the same as the mass of the helium that they created at the end. There are actually a tiny bit of mass missing, less than 1% of the total mass of the two objects together, but however, is not zero. Some of the mass is actually missing. The initial mass of the two hydrogen, right? So you have two mass of the hydrogen initially, is slightly more, okay, than the mass of the helium that you get at the end. So there's some missing mass. Now, what happens to that missing mass? That missing mass actually got converted into energy. Okay, that missing mass gets converted into energy. Now, and how much energy are we talking about? So let's say 1% of the mass is missing. That 1% of the mass per helium is converted into energy according to Einstein's E equal mc squared equation. So if you know how much the mass is missing, you just plug it into this equation, you can actually get out how much energy you're going to get from this reaction. This is nuclear fusion. This is actually how the sun has been burning for the past 5 billion years. So every time one of these reaction happens or occurs, you're going to have the sun losing a tiny bit of its mass. Now, it has been 5 billion years, so think about that. That means our sun is actually getting less and less massive every day. As a matter of fact, the sun is actually losing about 4 million tons of mass every second. The sun is always on. Some people will argue that the sun is not on at night. Well, it's not on for your side of the earth, but there's the other side, right? The sun is always on. So every second, the sun is losing millions and millions tons of mass. So eventually, it's going to run out of fuel, technically. But don't worry, the sun is a very massive star. The sun has a total mass of 2 to 10 power of 2 times 10 to the power 30 kilogram, which means if you, let's say you take that and you divide by the fact that it's losing 4 million tons of mass every day, every second, it will last for another 5 billion years. So by that time, we should be all gone. Right? We should be all gone. So nothing to worry about. Okay. So mass can be converted into energy. All right. So what does it have to do with moving really fast? Because up until today, we talk about time dilation, length contraction. All of those phenomena happen when an object is moving close to the speed of light, right? So we do have an equation like right here called mass increase formula. Now, and you see this familiar term, that is the gamma term, right? So remember, gamma is the 1 over v squared over c squared term. That's the gamma term. So we have this familiar term. So what does this equation tell us? Is that the mass of a moving object. Now, so if the object is not moving, it's going to have this mass called rest mass. That means, let's say you weigh 60 kilogram, right? You weigh 60 kilogram right now. That's your rest mass because you're not moving. But let's say you started to accelerate because you have some type of special power that you can actually go very, very close to the speed of light. Then the faster you run, the more your mass will actually increase. Okay, so you can have this relativistic increased mass when you're running really fast. When you're at rest, you have the rest mass. When you're running really fast, you have the increased mass from special relativity. Okay, so now let's look at why though. I mean, this is actually a weird weird way of thinking. So now, okay, so first of all, let's recap. How do we actually make anything move? So in order to move an object, we need to apply kinetic energy, right? So in order to move an object in physics, we need to give the object kinetic energy, right? If you remember that. So if I give you kinetic energy, then you go faster and faster. Now, so here's the two scenario. Under really, really low speed, most of the energy that you add to the object will actually go into increasing the object's velocity. So the object will go faster and faster. Okay? However, a tiny bit of those energy that you're adding into the object, the kinetic energy you're adding, will actually be converted into mass. So the object will become a tiny bit, a little, okay, so the object will become a little more massive. Now, the effect is really, really small. Okay, so let's recap this. At low speed, when you add energy to an object to move it faster, most of the energy will actually end up moving that object faster. So the object will go faster. However, a tiny portion of the energy that you are giving up to the object will be converted to mass and the object will become slightly heavier. For example, in this situation, let's say I have a 100-gram object which originally is not moving that fast. So let's say originally is moving at so let's say it's a 100-gram object originally moving at, let's say, 20 meters a second, right? So, and then I'm going to add like 1,000 joules of kinetic energy into it. So 1,000 joules of kinetic energy. And then what happened is the object is going to pick up speed. So pick up more speed. So it will be going even faster, right? So I add some kinetic energy into it. And then what happened? So the mass of the object. Now, so first of all, let's talk about the speed. The speed of the object is going to be increasing. So for example, from 20 meters per second, the speed of the object is now, let's say 25 meters per second. So there is a significant increase in the speed of the object. Now, how about the mass though? The mass of the object will also increase slightly. So maybe before it's 100 gram, now it's 100.00001 gram. So not all of the energy is going into increasing your speed directly. A tiny portion of the energy, a tiny bit of it, is increasing mass, not increasing speed. Okay, so a tiny bit is increasing mass. Most of the energy is increasing your speed. So you go a lot faster with your mass increased by like a tiny bit. Okay. Now, but what happens when an object is already moving at very close to the speed of light? Or the object maybe start off slowly, but then it's picking up speed so that it is actually going almost at the speed of light. So in this case, at high speed, most of the energy will actually go into increasing the object's mass instead. Okay, so you're going to get most of the energy for increasing mass, and very little of the energy will actually make the object go faster. Now, and the reason why is because a heavy object is very hard to accelerate. Try pushing a basketball is easy. Try pushing a dinosaur with the same energy is really hard, right? So now this object right here, 100 gram, moving at 95% of speed of light already. And I'm going to add 1,000,000 joules of kinetic energy to it. Sure, why not, right? Let's do that. Now, the object, of course, is going to speed up, right? So, of course, it's going to go faster because I'm giving it energy after all. So, it will go faster. But the effect is very, very small. So, the object will only go a tiny bit faster. So, from 95% of speed of light to 95, for example, right, to 95.001% of speed of light. So, it only increased slightly. Now, where does most of the energy go? So a tiny bit goes to increasing speed. So where does most of the energy go? Well, if the energy is not increasing speed, then the energy is increasing mass. So if you look at the mass, the object is going to become a lot more massive. So maybe from 100 gram, it become 60,000 gram. Okay, so it become very, very heavy. So when an object is moving slowly, any energy you add into it will make it go faster, noticeably faster. But when an object is already moving very close to the speed of light, any energy that you add into it, yes, it will increase your speed. It will still make you go faster, but most of that energy will convert into increasing the mass of the object. Now, when an object is really, really massive, it becomes super, super hard to actually make it go even faster. So, mathematically, you can actually see in this diagram. So I have this graph right here, which is versus velocity. So in classical physics, you can increase your velocity as much as you want, and there's no limitation on that. But in special relativity, we know that speed of light is the limit and you cannot go over it. So what happened to an object's mass? Well, it goes like this. For the first like 80-70% of speed of light, and as you increase your speed, your mass remain relatively stable until you get very close to the speed of light, and then suddenly your mass increase very, very rapidly. So as you get really, really close to the speed of light, your mass will actually tends to infinity. Okay, so that means even though you only weigh about, let's say, 80 kilograms right now, if you are moving at 99.9999% of speed of light, you have the same mass as this entire galaxy. And at that point, nothing is powerful enough to accelerate you anymore. That's actually one of the reasons why, again, why you cannot actually travel close to the speed of light or at the speed of light, because you will become infinitely massive. An infinitely massive object require infinite amount of energy to actually accelerate, and there is no infinite amount of energy. Okay, so here's another example. So I have a person in here pushing a basketball. He's going to feel like, okay, so this is just a basketball because the speed is relatively low, 10 meters per second, right? But when the basketball is traveling at, let's say, 99.99% of speed of light, that person trying to speed up the basketball even more is going to feel like, oh my God, what am I pushing? Gosh, right? I'm pushing a elephant, dinosaur. So now let's sum up all the equation at this point before we move on and do a couple of examples. So technically speaking, all three of the special relativity equations have almost exactly the same look. It's gamma something. Now remember the gamma factor, right? 1 over square root of 1 minus v squared over c squared. So there is the time dilation, which is the first thing we learned about slowing down the time when an object is moving close to the speed of light. And there's also the length contraction when an object is moving close to the speed of light again. Its length contracts in the same direction as its movement. And then, right now, today, the third one, mass increase. An object that's moving faster and faster close to the speed of light will have increased mass. So all three together, that means if you're moving close to the speed of light, your time slows down, so you age slowly, your length contracts, so you get skinnier, but then your mass increase, so you become really heavy. So you are a really heavy, skinny, long-living person, I guess. Now, so let's look at the next part. So as the object becomes more massive, right? So as the object becomes more massive, it becomes harder to move even faster. Given it even more energy, we'll only move it a little bit faster, but we'll make it even more massive. So in order to make an object travel at the speed of light, you will need infinite amount of energy, which is not possible. So therefore, no object that has mass can ever travel at the speed of light. That's the rule. If you have mass, any mass at all, even if you're an electron that has like 0.00 something gram of mass, you still cannot travel at the speed of light. There's only one object that could: photon. Photon is the only massless particle, and it must travel at the speed of light. Anything else, its speed must be slower than the speed of light. So if you are a beam of light, there is no other speed for you. Your only available speed is the speed of light, 3 times 10 to the 8 meters per second. But if you're anything else, electron, proton, neutrons, you will travel lower than the speed of light. Okay, so just a couple of examples. These are relatively easy. So let's see this first one. Calculate the mass of an electron when it has a speed of that in a cavalry tube of a television set. So now if your speed, so usually what I do, right, with this is I want to know the gamma factor first. So I have the speed over there, so I can actually get the gamma factor. So 1 minus v squared over c squared. Now in this example, they're actually giving us, as you can see, the speed. So we cannot use a shortcut. We have to actually type the speed in like this over c squared, which is 3 times 10 to the 8. Now remember, both of these are square, and then there is a giant square root on the outside. Okay, so that's going to give you a gamma factor, and then we can do the actual equation, which is the mass is the gamma factor multiplied by the rest mass. Okay, so the mass of electron. So the mass of electron, so electron mass is, so you could pick the gamma factor, which is whatever this is, put in here, and then multiply by the mass of electron, which is 9.11 times 10 to the negative 31 kilogram. Actually, I just recalled that from my memory. Someone double check. Okay. Now, so that is going to be increased slightly. So that really isn't moving that fast, right? So, so it goes from 9.11 to 9.19. Okay, so 4 times 10 to the 7 is about 12% of speed of light. So 12% of speed of light, your mass increased from 9.11 to 9.19, so not that much of an increase, right? Okay, so now let's look at what happens if you have a faster moving electron. So if the electron is moving faster, so this electron is moving at 98% of speed of light. Now this is a created inside a accelerator, particle accelerator. So in this case, v squared c squared. Now remember the shortcut that we used. So this one you can actually do that. So it's 1 minus 0.98, 98% of speed of light, and the speed of light cancels out. So that your gamma factor again. I don't have a calculator at hand, so I'm gonna leave the answer like that. And then we're gonna get the mass, gamma factor, rest mass again, and the mass of the electron is the same. So if you go through this calculation, you can get 4.58 times 10 to the negative 30 kilogram. Okay, so a lot heavier, 10 times heavier. All right, so 98% of speed of light. Now, this equation, next question is actually trying to do the reverse case. So it should be fairly easy also. So question 2, a particle, right now the mass is 1.6 times 10 to the negative 24 kilogram, but it's traveling at 65% of speed of light. What is its rest mass? Okay, so this is actually backward. That means this mass right here is the increased mass. We're looking for the rest mass. So mass increase is gamma, rest mass, like that. And we're looking for the rest mass. So they're giving us this one. So with the 65% of speed of light, we are going to use that to get the gamma factor. And the gamma factor, that one I have it calculated in here. Gamma factor for this one is about 1.316. So it's about 1.316. And then, so that means the mass, so that become 1.316. And then rest mass, which is what we're looking for. Now, so let's put the actual mass in here, which is 1.6 times 10 to the negative 24, and divide both sides by that. Algebra. So you're a great troll. I'm not going to do algebra. So you do it. 1.22 times 10 to the negative 24. That's in kilogram. Okay, so of course the rest mass is less heavy than the increased mass, right? It makes sense because when you go faster, your mass increases. So this is your original mass of the object when it's not moving. When it's moving, it becomes 1.6. Okay. All right. So one more. Okay, so this one is, at what speed do you have to travel so that your mass is actually double? Increased by 100%, which means you are doubling your mass. So what I want to do is this. So gamma. So what I want is just double, right? So let's say this is 2 kilogram, and I want that to be 4 kilogram, like that. Now when you divide that by both sides by the same amount, by 2, for example in this case, if you divide both sides by 2, you're going to get 2. So you want something that will make gamma equals to 2. Right, 2 equals to gamma. So gamma is just the factor 1 minus v squared over c squared. So how do you deal with that? Square both sides. That's the first thing I'll do. So you get, after you square both sides, you no longer have to deal with the square root on the right. And then you do a switch between these two terms. Then you get 1 minus v squared over c squared equals to 1 over 4. And you do a addition, subtraction, switch those two terms. So you get 1 minus 1/4 equals to v squared over c squared. Now, at this point, you can take a square root on both sides to get rid of the square on the v squared c squared. You're going to get approximately 0.87 equals to v over c. Multiply both sides by c, 0.87c. That means 87% of the speed of light. So that's how fast you have to travel if you want your mass to be double, right? So let's say you weigh 80 kilogram right now, and you want to weigh 160. You want your mass to increase to 160 kilogram. You need to travel at least at 86% of speed of light. Then your mass will double. You can actually increase it to any arbitrary number that you want. For example, you can have a similar calculation, but then you can say, well, how fast do I have to travel so that my mass is going to be the same as, let's say, the Statue of Liberty in New York, right? So you can increase it to any number you want. All right, next one, last question. Momentum. Oh, suddenly we're doing momentum. How? Well, because momentum and mass is related. Now, momentum normally is mv, right? So momentum equals to mv. So, but what about relativistic momentum? Well, then we only have to do one thing, which is making sure that this mass is the relativistic mass. That means instead of using the rest mass, use the increased mass in here. That's all you need to do. So therefore, relativistic momentum is actually gamma mv. Okay, so gamma m naught times velocity. This is the relativistic version. So when can you use the first version? This is when you're traveling slowly. When will you use the relativistic version? When you're traveling close to the speed of light. So this person is traveling at 90% of speed of light. So we're going to use this version on the right hand side. Okay, so 90% of speed of light, we're going to use this version. Okay, now as I guess we'll combine it together. So now momentum, and we want our gamma factor. So our gamma factor is 1 minus 0.9 square multiplied by initial mass 70 kilogram. So that's your rest mass multiplied by v, speed of light. You're not moving at 90% of speed of light. So 0.90 times 3 times 10 to the 8, because speed of light, right? So a lot of time we can cancel out the speed of light, but in this situation we don't want to, because we actually need to know exactly how fast that object is moving. So this is just the v, the velocity, and so this part is the velocity, this part is the rest mass, and this part is the gamma. Right, so gamma and v. Okay, so everything together, super easy. So 4.3 times 10 to the 10 kilogram meter per second. Okay, so that's the moment in the same direction that you're moving, of course. So that's the relativistic momentum calculation. So it's basically the same regular momentum calculation with a relativistic mass attached to it. All right, so at this point, then we have finished everything in this special relativity chapter. I think everything is done. So I will leave the detailed descriptions of what you need to do for this week's homework on the course webpage and on the portal. Goodbye, everyone. The next topic that we are moving into should be electrostatic. All right? Okay, so see you next week.